I have the feeling this SV08 will stir things up, but for now, the Sovol Comgrow T300 has been quickly becoming one of my most used favorite printers. So, before unpacking this SV08, which was delivered as I was recording this video, let's take one more look at my T300 because I've implemented the ultimate upgrade. No more gantry leveling ever. It was a bit of a challenge, but the results are well worth the little trouble. I'm excited to share the why and the how because these have implications no matter which 3D printer you are using. And once you know what I discovered, you'll be eager to try it yourself. The best part? It's simpler than it looks and incredibly affordable, under 25 bucks with shipping. So here's what we will cover today. First, the benefits of belting the Z motors, the necessity of connecting the Z towers and how it enhances stability, a comprehensive list of all the components and tools required for this upgrade, plus links where you can find them and order them together. And we will finish with a step-by-step walkthrough of the entire upgrade process. I'm Gergo, and welcome to Gergo Print 3D, the expanding YouTube channel dedicated to my 3D printing adventures and various DIY projects. And yes, the next video is on that SV08. Until then, I promise this will be interesting no matter what 3D printer you have. So let's dive into the reasons why this upgrade to the T300 is such a game changer in my opinion. The Comgrow T300, like many large 3D printers, has several motors that move the tool head up and down. But there's a catch. When these motors are not engaged, like after you've unlocked them or turned off the printer, they tend to drift apart. One ends up lower, the other higher, which means they need to be synced up before starting a new print. Otherwise, your first layer will not be straight. In this recent video, I introduced a method to level the gantry using the inductive probe and a smart 3D printed dial. This technique is faster and more accurate than the standard method of pushing the gantry all the way to the top. Printers like the SV07 and SV07 Plus have an edge here. They can level automatically because they can control the motors separately. Unfortunately, the T300 doesn't come with dual drivers, so it cannot level itself automatically, but don't worry, I've got something even better than automatic leveling, making leveling itself obsolete. By belting the two motors together, they stay in perfect harmony. When one motor turns, the belt ensures the other follows suit. I call this the ultimate upgrade because it makes our T300 superior to printers that adjust on their own. After all, no adjustment needed is faster and more efficient than automatic adjustments, right? With the T300's open access to the lead screws, its design naturally lends itself to connecting the Z motors. We can easily swap out the top knobs for pulleys and maybe add an idler to maintain tension, or so I thought. However, as I explored the upgrade, I stumbled upon an unexpected challenge. To select the correct belt, we need the exact distance between the Z columns. Simple, right? Just measure it. They are 365 millimeters apart. But here's the twist. When you raise the gantry, the distance changes. The gantry's movement causes the Z columns to shift slightly, with a noticeable difference of 5 millimeters on my unit. That's not trivial. This happens because the robust stabilizers in the back only reinforce the y-axis, leaving the x-axis vulnerable. Surprisingly, despite this play, my T300 didn't show significant Z-banding or any other ill effect, but this could even be a fix for those of you facing such issues. Regardless of that, to maintain belt tension, the columns must stay at a consistent distance. The T300 seems to be designed with this in mind too, featuring 4 pairs of screws atop each column, ready for a connecting bridge. Initially, I considered a fully 3D printed bridge, but there are 2 snags. The T300's build volume is too small for a single piece print, and even multi-part prints wouldn't withstand the stress. There are some amazing forces at play here. We'll need to bring some metal into the mix. And with this, we've reached the surprisingly short list of components you will need. A 6mm wide, 900mm long belt loop, the first standard size that I found that was sufficiently long. 2 pulleys with an 8mm bore, matching the T300's 8mm lead screws. 1 idler to keep the belt properly tensioned, a 3D printable arm, which you can print easily yourself. Moving on to the top bridge, you will need 2 500mm long right angle aluminum profiles, 25 to 30 millimeters maximum on one side and 20 millimeters on the other side, L-shaped and 2 millimeters thick. We'll actually only use 465 millimeters of it, but aluminum is a breeze to cut with a simple metal handsaw. You will need an electric drill with a 4 millimeter bit for metal, but don't worry, aluminum is so soft, even the most basic drill will suffice. And that's it. I'll provide links to these parts on AliExpress, where you can secure this entire kit for under 25 bucks, shipping included. Not listed are a few M4 screws, washers and nuts, which you likely have on hand, 3 M420 screws, 1 M412 screw, 2 washers, and 2 self-locking M4 nuts. If you're missing these, that's not a problem either. I'll include a link to a handy set that will be very useful for your future projects as well. So, step 1. Let's begin with constructing the bridge. First and foremost, ensure the gantry is raised fully before taking any measurements. With the Z-axis at 350 millimeters, feel free to disengage the motors or even power down the printer. Start by removing the 2 pairs of screws on the back and mark the center of the screw holes on the aluminum profile from both directions, both lengthwise and depthwise. I recommend drilling first and cutting later, giving you some leeway if you make any mistakes measuring or drilling. Remember, it's crucial to keep the gantry raised during this process. Don't forget to drill a 4 millimeter hole in the center of each bridge piece as well. These holes must also align perfectly, as they will secure the tensioning arm. It's best to attach the rear half of the bridge before loosening the front 2 pairs of screws. If not, the top covers may shift, risking damage to the delicate dust cover spring stick. Proceed to mark the front bridge as well, but allow a bit more clearance between the front and the column to accommodate the screws for the dust cover strips. For securing the left side of the front bridge, the longer M420 screws are ideal because the spool holder goes there as well. Now, in step 2, it's time to print the tensioner arm. Given its vertical orientation, it's typically prone to Z-banding. However, printing it after bridging the columns should mitigate this issue, taking advantage of the increased stability already. You can find the model on Calibration 3D. PLA is fine for this part, but for added durability, I suggest using 4 walls and at least 20% infill. With vertical orientation, you won't need supports, maybe some brims. I've included my Orca Slicer project file for your convenience. For well-tested, reliable Orca presets and start-end macros, I highly recommend watching this earlier video of mine. Step 3, assembly time. Install the belt and the idler using the third M420 screw here. Next, attach the pulleys, but only secure the right side for now. The left pulley will be tightened after the final gantry leveling, which could be the very last time you ever need to do it. First, let's mount the tensioning arm. Use the shorter M412 screw in the front and one of the replaced M415 screws in the back. Remember the washers on the top and the self-locking nuts underneath the bridge. Holding the nuts with pliers while fastening the screws can be a bit tricky, but I'm sure you will manage. And be careful not to over-tighten the belt. We don't want to put undue stress on the lead screws, even though they are protected by bearings in the top cover on both sides. Step 4, with everything in place, it's time for our final Z-tilt calibration. Although there is no dial to guide us this time, my macro will provide precise instructions, and after a few iterations, you should see the satisfying message, your gantry is level. I've included the macros in this Calibration 3D project as well, so there is no need to buy the Z-tilt knob project if you haven't yet. However, do check out that video to understand how those macros work. As you adjust the right pulley, the left one will rotate freely. This is essential for fine-tuning the gantry level. Only secure the left pulley once the gantry is confirmed to be level. And this marks the end of the process. And with any luck, it's the very last time you'll ever have to manually synchronize the sides. They are now connected in more ways than one. It's been a journey of months, making and discarding various designs, ordering and waiting for parts, testing and tweaking methods to bring you this fairly streamlined solution. It's a milestone I'm thrilled to share, simplifying both the number of components and the complexity of the process. I invite you to use the comment section below for any questions or suggestions for improvement. And if you're taking on this mod, be sure to check those same comments for any recent updates or corrections by the community. Now, if you've enjoyed the journey so far, please hit that like button, and I hope you're ready for more because we are gearing up for the assembly of the SV08. I'll post a video of it in a day or two. You can imagine my excitement. Make sure to subscribe for that, as well as upcoming content on the SV06 Plus, SV07 Plus and T300. I'm planning to compare and show you projects where we can use these printers together. Talking about these machines, you might want to check out these two videos next, or if you're feeling inspired, go print 3D. Get it? Gergo Print 3D? It never gets old.